far below you, an isolated mountain can redirect an ocean current without ever breaking the surface. Its summit may remain hundreds of meters deep, invisible to passing ships and absent from ordinary horizons. Yet water flowing around its slopes can rise, twist, slow, and gather living particles above the peak. Fish schools assemble in the altered flow, predators patrol the edges, and plankton encounter unexpected pathways. The mystery is how stone buried in darkness can reorganize life much closer to sunlight. These structures are seamounts, generally volcanic elevations rising prominently from the surrounding seafloor. Some form long chains above mantle hotspots, while others mark spreading centers, fractures, or extinct volcanic provinces. Their sizes, ages, summit depths, and shapes vary too greatly for one ecological rule to fit all. A steep cone in a swift current differs fundamentally from a broad sedimented rise beneath sluggish water. Still, every substantial seamount introduces topography where moving water previously crossed a deeper plane. That obstruction creates the investigation's central mechanism. Flow encounters relief, and the water column responds. Some responses remain confined near the bottom, while others extend upward through hundreds of meters. Biology enters wherever those physical changes affect food delivery, retention, shelter, or the cost of swimming. The resulting abundance can look like an oasis, but the word should describe an observation, not assume its cause. To explain life above, the mountain must be followed from rock formation into moving water and feeding behavior. Most seamounts begin as submarine volcanoes, building layers of lava and fragmented material on oceanic crust. After volcanism wanes, erosion, landslides, sedimentation, and subsidence reshape their summits and flanks. Some ancient volcanoes once reached the surface and were flattened by waves before sinking into flat-topped guyots. Hard rock provides attachment surfaces that differ from soft abyssal mud surrounding many isolated elevations. Deep corals, sponges, anemones, and suspension feeders can occupy slopes where currents deliver drifting particles. Cold water coral, Desmophyllum pertusum, forms complex habitat in suitable deep environments, including some elevated features. Its presence is never guaranteed because temperature, food supply, carbonate chemistry, substrate, and disturbance all matter. Above the rock, currents accelerate around flanks or separate into eddies where flow becomes unstable. Water can also be forced upward along a slope, carrying nutrients or suspended prey toward shallower depths. Whether nutrients reach enough light for additional phytoplankton growth depends strongly on summit depth and stratification. You imagine every seamount creating constant upwelling. Observations quickly expose the picture as too simple. Some generate strong local mixing, some produce intermittent wakes, and others show little surface expression. Rotation can organize flow into a trapped circulation over topography, sometimes described as a Taylor column. Such retention requires particular combinations of current, rotation, stratification, and mountain geometry. When it occurs, plankton or larvae may remain near the feature longer than surrounding flow would predict. When it fails, water and organisms simply pass over or around the summit. Multibeam bathymetry maps the mountain's shape by measuring sound travel times across the seafloor. Current meters record speed and direction, revealing oscillations, jets, and wakes through time. Water sampling measures nutrients and plankton around the feature, though a short survey can miss episodic events. Animal tags show how selected predators use the water column, but tagged individuals cannot represent entire populations. These methods connect rock, flow, and behavior while preserving uncertainty between measurements. Verified context, therefore, supports strong local effects, not a universal halo of productivity around every seamount. The mountain shapes possibilities, while weather, tides, currents, and animal choices determine what actually develops. First explanation to test is simple nutrient uplift, stimulating extra photosynthesis above the summit. This mechanism is plausible where upward motion carries deep nutrients into water, receiving sufficient sunlight. Researchers should then observe nutrient enrichment, followed by phytoplankton growth and a delayed response from grazers. Sometimes that sequence appears, but rapid flow, deep summits, or nutrient limitation can break it. The second explanation is prey concentration without any increase in total local production. Currents may compress zooplankton along fronts, trap them in eddies, or sweep them against slopes. Small fish detect the dense prey, enter the feature, and attract larger hunters through repeated feeding opportunities. This cue-action consequence chain can create spectacular gatherings from material produced somewhere else. The third explanation is vertical migration interacting with topography. Zooplankton descending at dawn may encounter a summit before reaching their usual daytime depth. Trapped above the rock, they become accessible to fish that anticipate or discover the concentrated layer. This process, often called topographic blockage, depends on migration depth, summit depth, and current timing. Predators arriving at dawn would support the mechanism, but coincidence alone would not prove anticipation. The fourth explanation is habitat structure supplied directly by hard slopes and coral frameworks. Juvenile fish may shelter among complex growth, feed nearby, and later move into the overlying water. This nursery interpretation requires evidence of survival and development, not merely the presence of small individuals. Each explanation predicts a different sequence, allowing observations to separate production, concentration, retention, and shelter. Yet several mechanisms can operate together, and their effects may change between spring tides and calm periods. Repeated dense schools confirm aggregation, but their presence does not show whether biomass grew locally. Confirmed recent feeding still cannot identify prey already digested beyond recognition. A brief chemical snapshot can misrepresent a wake moving faster than a survey vessel. Tagged predators show attraction only after researchers compare visits against routes and environmental conditions. The strongest conclusions emerge when physical changes precede coherent biological responses across repeated observations. Even then, a seamount may be important seasonally rather than continuously. One productive month can support migration or spawning without turning the feature into a permanent oasis. Unknowns remain especially large for remote peaks sampled once, and then generalized across entire ocean basins. The honest picture is a landscape of distinct mountains, each testing the same flow mechanism under different conditions. Life fixed to the mountain faces consequences from events occurring in the water far above. Suspension feeders extend polyps or filtering structures when currents deliver particles, then reduce activity when delivery weakens. Corals grow slowly in cold depths, so damage from heavy gear can outpace recovery by decades or longer. Bottom fishing may remove structure that concentrated invertebrates and offered refuge to associated species. If you protect only the summit, vulnerable communities along flanks may remain exposed to moving gear. Pelagic predators create a different management problem because their relationship with a seamount can be temporary and mobile. Tunas may circle a feature while feeding, then depart when prey disperses or water conditions change. Sharks can use seamounts during navigation, social behavior, or foraging, although motivations are not always directly observable. Seabirds sometimes gather over shallow features, where prey is driven upward within diving range. Their presence gives a surface clue to a mountain, but feeding birds cannot establish the exact subsurface mechanism. Whales may visit regions of enhanced prey, yet a single sighting proves neither dependence nor persistent productivity. These behavioral sequences connect deep relief with surface hunters through intermediate layers of prey. Seamount chains can also act as stepping stones for some attached organisms, dispersing across unsuitable deep plains. Larvae released into currents may reach another elevation, settle on hard substrate, and establish a separated population. Connectivity varies by larval duration, current pathways, distance, and successful settlement, making maps alone insufficient. Mining interest raises further stakes where mineral-rich crusts occur on exposed seamount surfaces. Removing those crusts would also remove habitat, create sediment plumes, and alter communities whose recovery is uncertain. Climate-driven changes in oxygen and temperature could shift which species can occupy summits or pass above them. Stronger stratification may reduce nutrient exchange across depth, changing the reach of topographic effects. The mountain remains fixed, but the water defining its ecological influence is already changing. Future evidence must begin with repeated measurements, rather than treating one expedition as a permanent portrait. Seasonal current records can reveal whether trapped circulation persists, reverses, or disappears during strong events. Coordinated plankton sampling can test whether observed concentrations reflect local growth or imported material. Longer animal tracks can show whether predators repeatedly return under comparable flow and prey conditions. Where closures exist, returning coral structure would support the expectation that reduced disturbance benefits fixed communities. Recovery should exceed comparable unprotected slopes before protection receives credit for broader regional change. Predicted zones of rising flow or particle retention must coincide with conditions actually recorded around the mountain. If you cross the same invisible summit years later, the rock will be familiar, while its biological halo may differ. One season may bring dense prey against the slope, and another may send currents cleanly past. Mixed corals record the long history of particle delivery, disturbance, growth, and mortality on the mountain itself. Passing fish record shorter opportunities, arriving when currents transform scattered food into profitable patches. Surface predators reveal only the final link in a chain, beginning where deep water strikes volcanic relief. No gathering alone proves that the mountain produced the life concentrated above it. The defensible conclusion is that seamounts reshape flow and habitat, sometimes concentrating or supporting life through mechanisms that remain locally variable. Their hidden influence is real, but its strength must be measured mountain by mountain, current by current, and season by season.